Hello dear students. I'm Vikas and I'm here to continue the Basics to Advanced series for NSEJS 2025. This series was earlier happening on the Vedantu Olympiad School YouTube channel, and now we have shifted this series on this channel which is dedicated to Science Olympiad, the Vedantu Science Olympiad channel. If you have not subscribed this channel already, please do that very soon. Do that very quickly, because on this channel we are going to bring you content that you will need for your NSEJS. Okay, now without wasting any time, let's continue. So the chapters that we are going to cover in this series are they are present in this sequence. You can have a look at this. Right now I'm going to start with laws of motion chapter. Okay, till the time it was happening on just a minute guys. Okay, I think there is some issue. Okay guys, I think I need to address this. Okay. I think I need to call my team member to address this. Just a moment guys, just a moment. Okay guys, you all can hear me? Yeah, hi Dutta, good evening. I think I ran into some kind of problem with... Okay, I can manage with this. Yeah, fine, I'll manage with this. Okay, so what we are going to cover in this chapter is the statement of the Newton's laws of motion. So Newton gave 3 statements and they form the fundamentals of this entire chapter. And not only this entire chapter, but the entirety of mechanics. So we are going to have a look at those statements. Very precise statements, very short, sweet statements, but they reveal a lot of things to us. Okay, so that is what we are going to do. Okay, and then we are going to cover the common forces, the FBD, the blocks, string pulleys, pseudo force, and spring balance. So these are the things that we will cover in this chapter. Let's begin, guys. And before we do that, if you have not subscribed to the channel yet, please do that. Okay, so first of all, we are going to talk about the statement of the first law. Okay, now this law states that any particle which is at rest or in a state of uniform rectilinear motion continues to do so unless acted upon by a force. I'll show that statement to you. So it says a particle continues to be in a state of rest or of uniform rectilinear motion unless acted upon by a force. Okay. So first of all, I would like you guys to copy this statement in your notes, and then we will start understanding this statement. Okay, there is a lot of things that are to be discussed as far as this statement is concerned. So let's start talking about it one by one. So first of all, what does the statement says? It says that if there is something, let's say particle, okay, if there is a particle and if this particle was at rest, okay, if it wasn't moving, it will not move until a force is applied on it. Okay, and suppose if it was moving with some speed, let's say 5 meters per second, then it will continue to move in the same direction with the same speed unless a force is applied on it. So essentially this statement tells us that whenever we are trying to produce acceleration, we need force. For example, if a particle is at rest, we are trying to bring it in motion, we need force for that. A particle is traveling in a straight line with a constant speed, we need to change the speed, we need force. We need to change the direction, we need force. So whenever we are trying to bring acceleration in the particle, we need force. Okay, so this statement actually, it tells us about the role of force. Okay, it gives us a qualitative description about what force can do. Force can produce acceleration is what we learned from this statement, but there are a lot of other things to be learned. Let's have a look at those. So what are the comments that we want to make? Okay, so the first comment is that it introduces us to the concept of inertia. Now what is that? Okay, so guys, inertia is inherent property of a particle to maintain its state of rest or of state of motion. So basically this is the definition. It says that it is the inherent property of a particle by virtue of which it tends to resist any change in its state of rest or of uniform motion. There are 3 types of inertia that we define, and those are inertia of motion, inertia of rest and inertia of direction. Okay, I'll give you an example of all this, all the three you will understand. So for example, suppose you are standing in a bus. Okay, so your entire body is at rest. Now as soon as the bus moves in the forward direction, you are standing in the bus. Okay, you're not sitting in the bus. As soon as the bus moves in the forward direction, you feel as if you are going to fall backwards. Okay, so what exactly has happened? Let's say if this is the bus, and you are standing here. Okay, so when the bus moves, what happens is that your feet, which is in contact with the bus, they also move forward, but your upper body is trying to maintain the state of rest because of the inertia. Inertia means resistance. Okay, so it is trying to maintain its state of rest. Okay, and therefore your feet move forward, your body is still there, and we get the feeling as if we are falling back. The reality is that our feet have moved in the forward direction. So this is called inertia of rest. Okay, what is inertia of motion? The same thing you experience if this moving bus, okay, when the driver applies the brake suddenly, our body tends to fall forward. Okay, that's because our body was in motion and our body tries to maintain the motion. When the bus driver applies the brake, the bus slows down. Along with the bus, our feet slow down and our body continues to maintain its state of motion, and therefore we feel as if we are falling forward. Okay, and then what is inertia of direction? So when the bus, the same example, when this bus takes a turn, we feel as if we are falling outwards. Okay, I'll show that. Okay, like I'll try to explain that using a figure. So suppose this is a turn, this is a right turn, and we are looking from the top. Let's say we are sitting in a helicopter and we are looking from top. Okay, now suppose the bus is going in this direction, and as the bus makes this turn, we tend to fall outward. We feel as if we will fall towards the outer edge of the turn. The reality is that our body tries to maintain the direction. The bus has turned already, but our body tries to it tries to maintain the direction of motion, and therefore we feel as if we are falling outwards. Okay, so this is about inertia. So what is inertia? It is the inherent property of a body of a particle by virtue of which it tends to resist any change in its state of rest or of uniform motion. And there are three types of inertia that we define. So the first law introduces us to the concept of inertia. It tells us that there is an inherent property in the body to maintain its state of rest or of uniform motion. Okay, so that is regarding inertia. Now the second point is that it introduces us to the concept of inertial and non-inertial frame. Now what is this? Okay, so if I go back to the first law, if I go back to the statement of the first law, it says that a body continues to be in a state of rest or of motion. Now guys, the moment I say that there is a state of rest or there is a state of motion, it becomes imperative for us to think about the reference frame. From where are we observing the object? Because rest and motion, these words depend upon the frame of reference. So if I'm using these words in my statement of first law, I need to tell from where am I observing the entity, the particle. I'm saying that a particle continues to be in a state of rest. So if the particle is appearing to be at rest to me, I must be observing it from somewhere. So which is that frame? Okay, so when we are speaking this statement, when we are giving out this statement, we have automatically, we are sitting in some reference frame. Okay, so we must talk about that. So guys, there are reference frames in which the Newton's laws, they are directly applicable without us requiring any kind of modification. Okay, such frames are called inertial frames. I will repeat, there are frames in which we can apply Newton's law without any kind of modification. Such frames are called inertial frames, and the identity of these frames is that their acceleration is zero. Okay, the acceleration, like how do we identify whether a frame is inertial or not? So the acceleration of the frame itself would be zero. Such frames are called inertial frame. Okay, now there would be frames in which we will not be able to apply Newton's law directly. Okay, such frames are called non-inertial frames, and the identity of non-inertial frames is that they are accelerated frames. Okay, so inertial are the ones which are non-accelerated, and non-inertial are the ones which are accelerated. Inertial are the ones in which you can directly apply Newton's law without making any changes to it, and non-inertial ones are the non-inertial frames are the ones in which you can use Newton's law, but then you need to make a small modification before you start applying the Newton's law, and that small modification is application of a hypothetical force. Like whatever we are doing, we consider an extra force in our calculations. This force is called the pseudo force. We'll talk about it later. But yeah, so whatever we are saying, okay, it may be applicable from a frame, it may not be applicable from a frame. We need to be clear that we are observing the entity from which frame. Okay, and so inertial frames are those frames in which Newton's laws can be directly applied without any modification. The identity of such frames is that they are non-accelerated frame. And then if I talk about non-inertial frames, they are those frames in which Newton's laws cannot be directly applied. The identity of such frames is that they are accelerated frames. We need to use an additional force called the pseudo force while analyzing such situations from the non-inertial frame. All right, so are we good with this, everyone? Okay, are we good with this? Okay, Siddharth is continuously messaging about a ray optics class. I don't understand why it is happening. Like, Siddharth, why are you expecting any ray optics class? On which platform are you expecting? So that's actually confusing me a bit. Anyways, okay, so now the third, this I already spoke about, that first law identifies the role of force, what role force can produce. For example, we discussed that force is needed to produce acceleration. What it does not tell us, what the first law does not tell us, is how much force is needed to bring about a certain amount of acceleration in a chosen object. First law doesn't tell us that. For that, we have the second law. Okay, so the second law says that the rate of change of momentum of a particle is proportional to the net force acting on it. Very simple law. It says the rate of change of momentum of a particle is proportional to the net force acting on it. So this force, this statement actually quantifies the force. It tells us that to bring about a certain change in momentum, how much force would be needed. So again, in this statement also, there are few things that we should talk about. We should talk about momentum. So what exactly is momentum? So guys, momentum is the vector quantity. Okay, it is a vector quantity which is denoted as mass times the velocity. So if there is an entity, if there is an object of mass m which is traveling with a velocity v, then the momentum of this entity is given by m into v. It's a vector quantity. Okay, so that's momentum. Now, if we talk about the rate of change of momentum, so what does the second law say? Second law is saying that the rate of change of momentum is equal to the net force acting on it. Okay, now watch this carefully. Momentum is what? Momentum is product of mass into velocity. So I can very well write it as m into dv by dt plus v into dm by dt. So momentum is product of two quantities. So if I have to differentiate momentum, I need to differentiate both the quantities one by one. That is the product rule of differentiation that we have used. Now notice here that if I say that this object is a constant mass object, like the mass of this object is not changing. For example, let's say we are talking about a ball, okay, or a particle. Okay, so if the mass of this entity is not changing, then dm by dt would be 0, and this would be the case with majority of the object, that their mass would not change. Okay, so now we can write that the net force will be equal to mass times of acceleration. Okay, so remember that this equation is valid when the mass of the object is constant. Now you will ask me, sir, mass is always a constant. Like, why are you saying that the mass is not constant? So guys, there may be situations in which the mass may not be constant. For example, rocket is a brilliant example of of a vehicle with variable mass. The major fraction of the mass of a rocket is its fuel. So as the rocket is going into space, as it is burning the fuel, okay, the mass of the vehicle is significantly changing. Okay, so this equation won't apply on a rocket. Okay, now you will say that, sir, the same should be applicable to motor vehicles also, the cars, the bikes that we see. So yeah, so in those also there is fuel and the fuel gets burnt, and yes, the mass does reduce. But the point is that if you think about a car, the weight of the car, the mass of the car would probably be in hundreds of kg, probably in tons. Okay, and the amount of fuel that we put in it is probably around 30 to 40 kg. Okay, that's how much the capacity of a car is, in liters. Okay, so that much mass is very small as compared to the mass of the car, and therefore even when the fuel burns, we can assume that the mass practically remains constant. Okay, so we are good to apply this equation for majority of the things, but whenever we see that the mass is changing significantly, we cannot apply this thing. Then we have to go back to this equation to solve. As of now, you can rest assured that this is what we are going to use. when this comes, this will come in momentum chapter. We'll talk about that at that time. Okay. All right. Now, I believe that part is done. Now we'll come to the third statement, the third law. Okay. Now guys, this is something that I've experienced, that any student who has ever studied science and who has ever had an exposure to Newton's law, that person remembers this law, no matter whether that person continues to study science or not. Okay, but anyone who has studied third law, they don't forget it. I'm pretty sure that you have come across this third law somewhere, already. If not, I'll tell you, but the statement is pretty simple. I think you already know it. The statement is, to every action, there is an equal and opposite reaction. Okay, a very beautiful statement, a very terse statement, very concise statement, and a lot of information is hidden in it. We need to talk about it. Okay, so first thing that I would like to mention here is that to every action, there is an equal and opposite reaction. Sometimes the teachers, I've seen teachers giving examples like, you asked your mama for a pizza and your mama scolded you because it is junk. So the act of asking for pizza was the action and the scolding that you got was the action, but that's a very poor example. If at all you have been given such kind of example, guys, when we say action and reaction, we do not mean an act. We do not mean an event. Okay, we are not saying that to every event, like whenever an event happens, something happens as a result of that event. No, we are not saying that. Action and reaction, both these words in this statement, they refer to forces. Okay, nothing else. The action here refers to a force and the reaction word here also refers to a force. It doesn't refer to anything else. This is not velocity, this is not momentum, this is not energy. Action and reaction, both these refer to forces. So what we are saying is that whenever there is a force, okay, there would be another force which would be equal and opposite to that force. Now, on which entity this force will act and all other things, we need to talk about that. But first and the foremost idea that we all must have is that the forces occur in pairs. Okay, so if there will be a force, there will be another force which will be equal and opposite to this particular force. So to every action, there is an equal and opposite reaction. Now, what have we not told here is this, or an alternative way to tell this statement is that if A is exerting a force on B, then B will exert an equal and opposite force on A. That would be an alternative way to tell the same statement. I'll repeat. If A exerts a force on B, then B will exert an equal and opposite force on A. Here A and B can be any entity. For example, A can be a charge, B can be another charge, like a proton and an electron. A could be a mass, B could be another mass. Okay, so if A exerts a force on B, B will exert an equal and opposite force on A. So that would be one of the statement. Okay, so I already told you that action and reaction are forces. Okay, if A exerts a force on B, B will exert an equal and opposite force on A. Okay, now the third point that you keep in mind, action and reaction, they never act on the same body. I have written never, never, never multiple times because I know that this is a point which confuses majority of the student, or this is a point that, majority of the student, they forget this point. There will be times when even you will draw the force and its reaction on the same entity, but no, if you read the previous statement, we are clearly saying that if A exerts the force on B, that means if the action is on B, then the reaction is on A. So action and reaction, they can never act on the same body. They always act on the different body. So please remember this. If A exerts a force on B, B will exert a force, equal and opposite force on A. So action and reaction, they never, never, never act on the same body. Another point, in a pair, in an action-reaction pair, if I ask you that which force acts first, what will you say? Think about this. Okay, if you are saying that obviously the action has to happen, only then the reaction will happen, then you are wrong. Okay, that is not the situation, guys. In an action-reaction pair, you can choose to call any one force as the action and the other will be called as the reaction. They happen simultaneously. Okay, so they happen simultaneously. They are always act simultaneously. Action-reaction pair, they always act simultaneously, and not only this, their line of action is also same. Okay, their line of action is also same. What does that mean? So if action force is acting like, if this is action, then reaction cannot act like this. Like it cannot be on a different line. It has to be on the same line. Okay, it has to act on the same line. So action and reaction, they always act on the same line. All right. So this is as far as the action reaction pairs is concerned. Okay, I hope you got the entire point. I hope you got the all the three laws. I made you, I told you a number of theoretical points that you need to keep in mind, guys. So before we jump into the calculations, the more interesting aspect of this chapter, these are the basic concepts that you need to remember. There will be times when you will be confused regarding what to do. And these basic ideas, if you remember, then you will be able to sort out your confusion. You'll be able to find an answer to any kind of confusion that you are having. Okay. Now, if we come to force, okay. If we have to define a force, what exactly is a force? We may choose what kind of definition we may want to give. A very simple definition would be, it's just a push or a pull. Okay, that's quite simple. It's a push or a pull, not too technical, I would say. Okay, but if we want to go a bit more technical, okay, then force is that physical cause. Okay, a force is that physical cause which produces acceleration in a particle. Okay, if we are thinking about a particle, if we are treating the object as a particle, then that is enough. But if we have an object, then we would say that for an object, a force can either produce acceleration in it or it can deform the object. Okay, or maybe both. Okay, so that would be force. Now, if I talk about the common forces, okay, so the common forces that we have to deal with, okay, common forces. I'll start with the most common one, okay, mg, or the weight. Okay, this is the most common force that we would be dealing with. So let's talk about this force. So first of all, who exerts this force? Okay, so this force is exerted. This force is exerted by Earth. Okay, this force is exerted by Earth. Fine. Okay. So every object that has mass m, okay, every object or particle, okay, every object or particle that has mass m experiences this force. Okay, so any entity with mass will experience this force. Okay, and then the direction of this force is vertically downward. Okay, its direction is vertically downward, and its magnitude is mg. If the object mass is m, then the magnitude is mg. So direction is vertically downward and magnitude is mg. Okay, now what does that mean? Okay, like when we say acceleration direction is vertically downward, what does that mean? So let's say if this is Earth, okay, if this is equator and this is the axis, this is North Pole. Okay, let's say that there is a person standing here, okay, maybe a giant person, okay, and I want to draw its weight, mg force. Okay, this would be the direction of mg. So when I say vertically downward direction is which direction? It is the radial direction towards the center of the Earth. Okay, so if the person is standing here, then mg force would be like this. If the person is standing here, then mg force would be like this. So a vertical direction is a radial direction towards center of the Earth, and horizontal direction is tangential. So at this point, this is horizontal direction. Okay, this is horizontal. Okay, at this point, this is horizontal. Okay, so keep in mind the idea of vertical and horizontal also. Usually things look odd only when we look at Earth from space. But if I say that, okay, this is ground and a person is standing here, things remain quite simple under these things. Mg force will act like this. Okay, so that's about mg. Okay, that's about mg. Now let's talk about the next common force. What would that be? We will talk about normal reaction. Okay, now normal reaction. So first of all, this normal word here, it does not indicate the general. Like normal doesn't mean general or ordinary here. Normal means perpendicular. Okay, so this is a force that acts when two objects are in contact. So it acts when two objects are in contact. Okay, it acts when two objects are in contact. That is first point. Second point, it is a pushing force, which means the two objects in contact will try to push each other. Okay, normal force cannot pull things. Okay, so it is a pushing force. And the next point is that it always acts perpendicular to common contact surface. Okay, this last point I will explain with examples. Okay, so it is always perpendicular to common contact surface. Let me take some examples to explain this. Okay, so let's consider a situation. Let's say this is ground, maybe tabletop, and we kept a block on this. Okay, we kept a block on this. It's a horizontal surface, you can assume. Okay, now because these two entities are in contact, they will exert a normal reaction on each other, and the normal reaction is always the pushing force. So they will try to push each other. Okay, so the block will try to push the table downwards with some force. Let's call it as N1, and the table will try to push the block upward with the same force, N1. So these are the normal forces that they will exert on each other. This one indicates the normal force on the table by the block, and this arrow indicates the normal force on the block by the table. See how they are trying to push away each other. Okay, and why did I draw a vertical arrow? Because the common contact was horizontal. So the normal force needs to act perpendicular to the common contact area. Okay, let me take another example which will probably highlight things better. Okay, so let's consider this as a horizontal surface, and let's say on the horizontal surface there is a block A which is kept like this, and there is another block B which is kept like this. Okay, now I want you to think about the normal forces that you would be drawing on B. You can start by thinking about the count of normal forces that we should be drawing on B. Can you tell me how many normal forces will you draw on B, guys? Okay, because B here is in contact with two entities. It is in contact with A, it is in contact with ground. So every contact will lead to a normal force. So B will be acted upon by two normal forces. Okay, now here if I try to draw the normal force, we have a corner of B, and at corners we can't draw normal, we can't draw tangents. So which direction should I call as the normal? So what you do, B is in contact with the floor, and this is the region where B is in contact with the floor. So you may not be able to draw the normal at B, but you can still draw the normal at this surface. So on B, this would be the normal force exerted by the surface. Similarly, normal force exerted on B by A would be this much. Okay, so these two arrow indicates the normal force on B. If I want to draw the normal forces on A, how will I draw them? I'm drawing it separately to keep the figures clean. Okay, so the reaction of N2 will act like this. I will still name it as N2 because action and reaction, they have the same magnitude. Okay, and there will be another normal force on A exerted by the ground. Okay, if I want to talk about the normal forces on the ground, okay, so normal forces on the ground, that is because of A, so that would be N3 in this direction, and of course there would be another M1 that B is exerting. So these would be the normal forces that we will draw. Okay, so that is about normal force. So we have talked about mg, we have talked about normal force. Okay, another common force that we can talk about is tension in a string. Okay, we can talk about tension in a string. Okay, so guys, basically it is the force exerted by a string. Okay, it is force exerted by a string. Tension is always a pulling force. What does that mean? You can't really tie a thread to someone and then you can push that person using the thread. the thread will fall loose if you try to do, but you can still pull the person using the thread. So the force exerted by thread, okay, that is the tension, it's always a pulling force. Okay, let me show you how we draw the tension. Before that, there is another point to keep in mind. You know, there are few things that I will make clear as we move forward. For now, you can just assume that we will be dealing with massless and smooth strings. Okay, if I remove this condition, things will change. But to keep things simple and to begin with, let us assume that the strings are massless and smooth. What is the advantage here? Okay, or let me show things to you. Okay, so if I say that there is a block which is hanging via a thread, you know, there is a thread using which we have suspended a block. Okay, now obviously the string is in contact with the block, so the contact force between string and the block will be indicated by tension. How do we draw the tension? So wherever the string is touching the block, from that, if the string tries to pull, the string will pull it towards itself. So draw an arrow on the string, that is your tension. Similarly, is the string pulling the ceiling also? Yes, the string is pulling the ceiling down. So if I were to draw the tension on the ceiling by the string, okay, this is tension on the block by the string, this is tension on the ceiling by the string. Okay, and these are not action reaction pair, mind you, these are not action reaction pair. Okay, both these forces, this arrow indicates force on the block, this arrow indicates force on the ceiling. Both of them has been exerted by the string. So these are not action reaction pair. Okay, I'm just trying to show you that wherever string touches an entity, from that point we have to draw tension forces. Okay, and these two tensions could have been different if the string would be having some mass. The condition that the string is massless allows us to assume that tension between two contact points of a string will remain same. So if you are assuming it to be T here, you can assume it to be T here. Okay, let me take a little bit more complicated example to explain. Okay, suppose I draw a pulley like this. Okay, and then I say that, okay, there is a string hanging from the two sides and there are blocks like this. Okay, let's say this is M1, let's say this is M2. I'm interested in drawing the tension forces. Okay, so the tension on block M1 will be in the upward direction. Okay, the tension on M2 will also be in the upward direction. The tension at this point, or you can say the tension in the pulley, will be in downward direction and downward direction here. Because we said that the string is massless, we can declare these two tension to be same and these two tension to be same. Because we said that the string is smooth, therefore we can declare these two also be same. So in other words, if I call it as T1 and T2 and this as T3 and T4, okay, then what we are saying is that T2 is same as T1 and T3 is same as T4 because the string is given to be massless. Okay, and T2 is same as T4 because the string is given to be smooth. So the conditions that we have given us, they allow us to equate. So after all this, all the four tensions become equal. Okay, now we have talked about the common forces. Okay, next thing that we need to talk about is how to draw the FBD. That is the most important step in the entire mechanics, guys. Okay, the students who master this step, they generally don't face any kind of trouble in the entire mechanics, but generally the weakness in a student is because they don't think about the proper FBD, they don't draw the proper FBD. So let's try to understand what is an FBD. So guys, FBD stands for free body diagram. That is what an FBD is. It's a free body diagram. Okay, that's the full form. What does it indicate? So when I am thinking about the motion of a certain object, for example, I just drew a block on the pulley, so I may be thinking about the motion of a block. So whenever I am trying to analyze the motion of a certain entity, I need to consider all the forces acting on it. Okay, I need to okay, someone is saying English mein bolo. Bache, Anand sir is taking sessions in English on the same topics. So I don't think that you know, I am specifically here to cater to students who find it difficult, who find who find it difficult to understand Hindi. So this will continue in English only. The Hindi sessions are happening at 8 p.m. in this same channel. Okay, so if you wait till 8 p.m, probably today physics session will not happen. Tomorrow physics session will happen at 8 p.m. That will be in English, so you can see that. Okay, now coming back to what is the free body diagram. So once you have decided that you want to make, think about an object, then we make a free body diagram. I'll explain it with example. So let's say there is an inclined surface and a block is kept on it. Okay, let's say that is the situation. Okay, rather let me do something. Let me take it different, because here friction would have come into picture. So let's say there is a mass, and this mass is hanging like this from two strings. Okay, and we know that this angle is, let's say, 37 degree, and this angle is, let's say, 53 degree. This is mass M. Okay, suppose I want to draw FBD of the mass. So what are the steps? Okay, what are the steps to draw FBD? Okay, the first step is encircle the body. Okay, the first step is encircle the body. For example, I will put my pen here, and then I will make an enclosure in which only that object will come, the FBD of which I'm trying to make. Okay, what this step helps us with, or this exposes, okay, this step exposes all contact points. So in your bid to encircle this object, you would be cutting these strings. Okay, like your pen will move through the strings. So every time you are cutting a contact with anything else, a contact force will come into picture. So this will expose. So I now know that I have to take care of two contact points, two contact forces. Okay, so next step, you can draw the contact forces. Okay, next step, you can draw contact forces. Okay, so if this is the block that I segregated, okay, I will draw a contact force here. Let's say T1, I will draw another contact force T2, and these forces will be along the string. So this one will be 37 and this one will be 53. And then as the next step, you can draw non-contact forces. Okay, now in contact forces, what all entities come? In contact forces, you can talk about tension, you can talk about friction, normal force. Okay, in non-contact force, you can talk about mg. There would be electrical and magnetic forces also, but not right now. They will come later on. Okay, like when you do those chapters. So right now, the non-contact force is merely mg. Okay, and as a final step, as a fourth step, you can draw pseudo force if needed. Okay, so I told you about pseudo force, that we need pseudo force if we are analyzing the situation from a non-inertial frame. Right now, let's ignore that, so we don't need it. So this is your FBD. That finishes the FBD. Okay, that finishes the FBD. All right. All right, getting this? Okay, let me take another example. So if this, so there are four steps. Okay, let me take another example, maybe a better example. Okay, so this time, please pay attention to this example. Okay, this is a wedge, or basically an inclined plane with inclination theta. There is a pulley here. Okay, and then there is a string here, and then there is a block here. Okay, so this is the arrangement, let's say. Okay, there is no friction here. There is no friction anywhere. In this arrangement, if I decide that I want to make FBD of block, okay, if I decide that I want to make FBD of block, let's see how we will do it. Okay, so the first step would be to encircle the block. When I encircle the block, I move my pen around it. I notice that I have to break contact at 2 points, the thread and the surface. And therefore, when I sit to draw the FBD of the block, okay, I need to take care of the tension, the contact force, the normal force. So the contact forces are done. Non-contact force would be mg. Okay, so that finishes my FBD of the block. How to use the FBD is altogether a different thing. You know, we will learn that. But first we need to practice making the FBD, making the perfect FBD. So that is the FBD of the block right now. Okay, this is vertical, this is perpendicular to the incline, this is parallel to the incline. Now let's say if I talk about drawing FBD, instead of FBD of block, let's say I want to draw FBD of wedge. Okay, I want to draw FBD of wedge. So first of all, what you can do, any pulley that is attached to a wedge can be considered as part of the wedge itself. Okay, now I will encircle the wedge I'll put my pen here. I will not lift my pen, and see, to encircle the wedge, this is how I need to move my pen. And what are the contact points that I need to break? Here I broke the string, here I broke the string, here I broke the contact with the ground, here I broke the contact with the block. So if I draw the wedge here, okay, what are the contact forces that I need to draw? I will be drawing a tension here, I will be drawing another tension here. These are the two contacts that I broke. Okay, then I will be drawing a normal force from the ground, I will be drawing a normal force from the block. So these are my contact forces. As far as non-contact force is concerned, that would be mg for now. So that finishes my FBD. Okay, so guys, as we move forward, as things become more complex, you will find that in a single diagram there would be 10 to 12 forces that you need to take care of, and that is where situation gets complicated. Like if you are not following the proper steps, then there are two things that can happen. You can either omit a force that you need to draw in the FBD, or you may end up drawing the same force twice if you're not following the proper steps. Okay, so I've shown you how to follow the steps and make the FBD. Please always follow these steps, okay, until you become too good and you can then give up following the proper steps. But until that time, please keep on following these steps, and that will ensure that you are always drawing the correct FBD. Alright guys, so how to use this FBD is something that I will tell you in the next class. Okay, for now I will take your leave. I hope you enjoyed this session guys, and yeah, you will find me again next week on this channel at the same time. Take care students. Bye bye. Bye guys.